In this video, we're going to talk about relativistic dynamics, which is how things like forces, energy, and momentum behave in special relativity. We'll also derive the famous equation E = mc squared. In special relativity, we found that different observers disagree on many physical quantities, like time, space, velocity, momentum, and kinetic energy. In previous videos, we found that all inertial observers agree on the speed of light in a vacuum c and the spacetime interval s squared. In this video, we're going to introduce the idea of Minkowski vectors, also called 4 vectors, which are vectors in spacetime that all inertial observers agree on. In standard Newtonian physics, we're used to dealing with 3-dimensional vectors, which in this video I'm going to denote using small lowercase letters. We have 3-dimensional position, small r, which measures the x, y, and z coordinates of a point, and also velocity, small u, which is the derivative of position with respect to time, momentum, small p, which is mass times velocity, acceleration, small a, which is the second derivative of position with respect to time, and force, small f, which is the derivative of momentum with respect to time, which is also mass times acceleration if the mass is constant. In special relativity, most of these quantities aren't very useful because the time variable is measured differently in different reference frames. This means that every frame will take time derivatives with respect to a different time variable. Recall in the last video that we defined the spacetime interval s squared between two events. When s squared was positive, we said s is equal to the speed of light c times the proper time tau, which is the time between two events when they happen at the same position. So tau is agreed on in all inertial reference frames. Since all frames agree on the proper time tau between two events, they will also agree on derivatives with respect to tau. We can now define Minkowski vectors, or 4 vectors, which are denoted with big capital letters, using derivatives with respect to proper time tau. We start with the 4 position, big S, which is the 4-dimensional position in space-time. For velocity, big U, is the derivative of 4 position with respect to proper time tau. For momentum, big P, is mass times the 4 velocity. For acceleration, big A is the second derivative of 4 position with respect to proper time. And for force is the derivative of 4 momentum with respect to proper time, which is also mass times 4 acceleration if the mass is constant. We're going to find that all reference frames agree on these 4 vectors because they are invariant. Recall the idea of invariance from Relativity 102. If we write the same vector in terms of different basis vectors, we get different components. We've already seen this idea with the spacetime separation vector S, which is also called 4 position. And we can change between the components of S in different reference frames using the Lorentz transformation. In this video, we'll see that this is also true for any 4 vector, including 4 velocity, 4 momentum, and others. We can write the same geometrical vector with different components in different reference frames, and change between the components using Lorentz transformations. Now, our starting point for all these Minkowski vectors is the 4-position big S, which gives us the position of an event in spacetime relative to the origin. Big S has 1 time component, ct, and 3 space components, x, y, z. We can get the 4 velocity, big U, by taking the derivative of 4 position with respect to proper time tau. To calculate this, we expand big S into its components. Since we have the derivative of a sum of terms, we can just give the derivative operator to each individual term. Now normally, we would take one of these 4 derivatives and do product rule with it, getting a term with the derivative of the components plus a term with the derivative of the basis vector. However, in the case of inertial reference frames, basis vectors are constant everywhere in spacetime, so the derivative of a basis vector is 0 for inertial frames. In future videos, when we deal with non-inertial frames, we're going to see that these derivatives of the basis vectors are actually non-zero. But for this video, we're dealing only with inertial frames, so the derivative of the basis vectors are 0. So the derivative of 4 position s is another 4-dimensional vector containing derivatives of t, x, y, and z with respect to proper time tau. We can take the speed of light in a vacuum c out in front of the derivative because it's constant. Let's figure out what dt by d tau is. Recall the Lorentz transformation between a coordinate system ct tilde and x tilde to another coordinate system ct and x. Here, beta is just the fraction of the speed of light, u over c, and gamma equals 1 over the square root of 1 minus beta squared. Recall that the proper time tau between two events is the time measured between events in a coordinate system where the events happen at the same position. Let's say in the frame ct tilde and x tilde, these two events happen at the same position, so x tilde equals 0 between these two events. So given the Lorentz transformation equation for time, this means that if we set x tilde is equal to 0, then the time t tilde is equal to the proper time tau, because it's the time between events measured at the same position. So this term goes to 0, and we can cancel c from both sides to get t equals gamma times tau. So taking the derivative of t with respect to tau, we just get gamma. So we've determined that dt by d tau is gamma, and this helps us determine the first component in ds by d tau. But what about the xyz derivatives? Well, if we recall chain rule from calculus, if we have nested functions where t is a function of tau and f is a function of t, we can calculate the derivative of df by d tau by multiplying df by dt and dt by d tau. As an example, we can consider x of tau instead to be a nested function x of t of tau. We can then turn dx by d tau into dx by dt times dt by d tau. Of course, dx by dt is just the familiar velocity in the x direction we know from non-relativistic Newtonian physics. And I'll denote this velocity by small u with superscript x. And we already know from before that dt by d tau is just gamma. So the derivative of x with respect to proper time tau is just the ordinary x direction velocity times gamma. We can use this chain rule approach for all derivatives of space coordinates with respect to proper time, and this gives us the ordinary non-relativistic velocities with respect to the t coordinate times dt by d tau, which is just gamma. If we factor out the gamma that appears in every term, we see that the velocity ds by d tau equals gamma times the vector cet plus uxex plus uyey plus uzez, where the lowercase u denotes the non-relativistic velocity. So the derivative of the 4-position s with respect to the proper time tau gives us a new 4 vector called capital U, which is the 4 velocity. The components of the 4 velocity u are given by big UT, big UX, big UY, and big UZ. Remember, small or lowercase u denotes non-relativistic velocities with 3 components x, y, z with respect to t. The big or uppercase U denotes relativistic velocities with 4 components t, x, y, z with respect to proper time tau. We can also write the 4 velocity in array notation, with basis vectors in a row and the vector components in a column. If we multiply the arrays, we get first entry times first entry, second times second, third times third, and fourth times fourth, which gives us the original vector big U. So what's so good about this 4 velocity vector big U? The answer is that big U is invariant in all coordinate systems. Let's see this using an example. Let's say that Einstein is stationary in space in a space-time diagram, and a car is moving off to the right in the x direction at half the speed of light. So the non-relativistic velocity in the x direction, ux, is 1/2 c. For simplicity, let's say that the velocities in the y and z directions are 0, so we're only concerned with the x-axis and the time axis. The square of the total velocity of the car is normally ux squared plus uy squared plus uz squared, but since only the x velocity is non-zero, this means that the total velocity u is ux, which is 1/2 times the speed of light. This means that beta, which is u over c, is just 1/2. And for beta equals 1/2, the corresponding gamma coefficient is 2 over the square root of 3. The 4-velocity vector of the car has only two non-zero components, gamma times c for time and gamma times ux for x direction. Subbing in 2 over root 3 for gamma and 1/2 c for ux, and cancelling these 2's, we get that big U equals 2 over root 3 CET and 1 over root 3 CEX. We can see that the components of this 4-velocity vector match up with the direction of the car's world line in our space-time diagram. However, in the reference frame of the car's 3 velocity is 0, and this means that beta equals 0 and therefore gamma equals 1. In the car's frame, the car's 4 velocity equals c times et tilde. All of the space components are 0. Again, this matches up with the vector big U in our spacetime diagram. So we can see that the 4-velocity vector big U is an invariant vector. It has different components in different reference frames, but it is the same unchanging vector in spacetime. Also, notice that even though the car's ordinary non-relativistic velocity is 0 meters per second in its own reference frame, its 4 velocity is not 0. The car still has a non-zero 4-velocity vector component in the time direction. It's just that the spatial components of the 4-velocity are 0. Also, just as the components of the 4-position vector can be transformed to different frames of reference using the Lorentz transformation, the components of the 4-velocity vector can also be changed to a different frame using a Lorentz transformation. When we have a 4-velocity vector written in a basis in array notation with a row of basis vectors and a column of vector components, when the basis changes with one Lorentz matrix, the components change with the inverse Lorentz matrix. So the components of the 4-velocity vector big U transform just like the components of the 4-position vector big S. We can see that if we take the Lorentz transformation, plug the gamma and beta coefficients in, and also the ut and ux components in Einstein's frame, we get the expected 4-velocity components of ut tilde equals c and ux tilde equals 0 for the car's reference frame. But these components still describe the same 4-velocity vector u. Another thing to notice is that the quantity big U dot big U is also invariant and agreed upon in all reference frames. Recall that with a Minkowski orthonormal basis, the time basis vector dotted with itself gives +1, and a position vector dotted with itself gives -1, and mixed basis vector dot products are 0. So in our case, big U dot big U is ut squared minus ux squared. In Einstein's frame, this gives us 2 over root 3c squared minus 1 over root 3c squared, which is 4 over 3c squared minus 1 over 3c squared, which ends up just being c squared. In the car's frame, we can take this same formula and plug in the 4-velocity components for the car, which are c for time and 0 for x. This gives us the same result, c squared. It turns out that big U dot big U is equal to c squared for all 4-velocity vectors. All 4-velocity vectors have a Minkowski length of c, the speed of light in a vacuum. If you want to go through the proof, you can pause this video, but the basic idea is to write big U dot big U in terms of a basis, then distribute the terms, calculate the dot products, sub in the formulas for the U components, factor out gamma squared, and then do some cancelling, and we get c squared. So the Minkowski length of all 4-velocity vectors is c. So we've learned that the 4-velocity vector big U is just the derivative of 4-position big S with respect to proper time tau, and these are its components, and its Minkowski length will always be c. Let's take a look at another 4-vector, the 4-momentum, capital P, which is defined as the mass times the 4-velocity vector big U. This is similar to the definition in Newtonian physics, where 3-momentum equals mass times 3-velocity small u. If we expand the 4-velocity big U, we can see the 4-momentum big P written in a basis with components. So in some basis ET, EX, EY, EZ, the components of the 4-velocity look like this. And to get the components of the 4-momentum, we just multiply by the mass m. Now, I should say that anytime I refer to the mass m of an object, I'm referring to the mass when measured in its own reference frame. Some textbooks call this the rest mass, but I'm just going to call it mass. Now, I will warn you that some textbooks use a definition called relativistic mass, which I've written curly m, defined as gamma times the rest mass. Remember, since gamma is always greater or equal to 1, this means that the relativistic mass will increase with velocity. Now, the reason that some physicists came up with the idea of relativistic mass is that it makes the components of the 4-momentum vector look more like the Newtonian momentum that we're used to, where the spatial components of the 4-momentum are now just the relativistic mass m times the ordinary 3-velocity. However, it's my belief that we should try as much as possible to write relativistic equations using invariant quantities that are the same in all reference frames. So in this video series, I will not be using relativistic mass since it changes in each reference frame. Anytime I talk about mass, I'm talking about the rest mass of an object that is agreed upon in all reference frames. So looking again at the 4-momentum components, the spatial components of the 4-momentum look pretty familiar. They are just the Newtonian momentum, mass times velocity, but multiplied by the gamma factor. However, the time component of the 4-momentum, gamma times mass times the speed of light, looks more mysterious. To understand what gamma times m times c is, we're going to have to expand gamma as a Taylor series in terms of beta. Recall that the Taylor series of a function, f of x, is an infinitely long polynomial in x that approximates f of x. You might already be familiar with the Taylor series of e to the x, sine of x, and cosine of x. It turns out that the Taylor series for gamma as a polynomial in beta looks like this. If you want to prove this, you can calculate the coefficients by taking derivatives of gamma with respect to beta and then evaluating them at beta equals 0. Now recall, beta is just a fraction of the speed of light, u over c, so we can sub that in now for beta. And if we take the time component of 4-momentum and multiply it by c, we get m times c squared times gamma. If we expand gamma using the Taylor series that we talked about above, we get this. We can distribute the mc squared to each term in the series. Let's ignore the first term for now. In the second term, we see that we can cancel c squared on top with the c squared on the bottom. And the higher order terms in the series are not too important for now. So we found that we can write c times the time component of 4-momentum like this. The second term in the series is the familiar kinetic energy from Newtonian physics, 1/2 times mass times velocity squared. This seems to imply that all these higher order terms are new kinetic energy terms that Newton didn't know about. Note that because of the u over c terms in here, these terms only become noticeable at speeds close to the speed of light, so it makes sense that Newton wouldn't have known about them. And finally, the first term doesn't contain any velocities at all, so it must be an energy that all massive objects have even when they are at rest. So really, we found that c times the time component of 4-momentum gives us an energy term. It's the rest mass energy, mc squared, plus several additional kinetic energy terms. In other words, energy divided by the speed of light c gives us the time component of 4 momentum. So we now know the formulas for the 4 components of the 4 momentum vector. The time component equals energy divided by the speed of light, and the space components equal the Newtonian 3 momentum, mass times velocity, times the gamma factor. Also, since we know that the 4 velocity dotted with itself gives c squared, it isn't hard to calculate the 4 momentum dotted with itself. We just get m big U dotted with m big U, which is m squared times big U dot big U, which is m squared c squared. We also know that we can calculate the dot product of 4 momentum with itself using the Minkowski metric, where the time component squared gets a positive sign and the spatial components squared get negative signs. We already know from above that big P dot big P equals m squared c squared, and the time component of the 4 momentum is energy over c, and the position components are just the 3 momentum components multiplied by gamma. Now we can multiply all terms by c squared to get this, then move this momentum term to the other side of the equation to get this. And this is Einstein's energy-momentum relation. It relates the quantities of mass, energy, and momentum together in a single equation. Now, one special case of this formula is for stationary particles, when the non-relativistic momentum, mass times velocity, is 0. In this case, the formula reduces to the famous equation E equals mc squared. Remember, this only applies for stationary particles. Another special case is the case of a massless particle. If m equals 0, the above formula seems to imply that energy is also 0. But we know that light, which is massless, definitely carries energy, since the sun's light heats the Earth, so something must be wrong here. It turns out that the formula mass times 4 velocity doesn't work to get the 4 momentum of light. The reason is that the 4 velocity big U is not well defined for light-like position vectors. The proper time tau for light-like position vectors is always 0, so it doesn't make sense to take a derivative with respect to tau for a light-like position vector. And if we try to define the components of a 4 velocity vector big U for a light-like trajectory, we end up with ut equals plus or minus ux, so we get multiple solutions for what the 4 velocity components could be. So there really is not a good way to define what the 4 velocity is for light. So let's try to come up with a different way to define what the 4 momentum is for light. We know that the 4 momentum for light should be a null vector with a 0 Minkowski length. And this makes sense because the light's mass is 0. This means that the square of the time component of 4 momentum is equal to the sums of the squares of the position components for the 4 momentum. Now, we know that the time component of 4 momentum is equal to energy over c. And I'm going to write this combination of the squares of the spatial components of momentum as just big P with the subscript light, to indicate the momentum of a light beam. So for light, which is massless, the energy of light comes from its momentum, not its mass. And if you know some quantum mechanics, you'll know that light's momentum is related to its frequency, where higher frequencies give higher momentum and energy. So we've managed to define the 4 momentum both for massive objects and massless objects like light. Let's take a look at how the 4 momentum vector is invariant by looking at our example with stationary Einstein and the moving car. We already know the 4 velocity vector of the car in each of their reference frames, so we just multiply that by mass to get the car's 4 momentum. Note that in the car's frame, the car's 4 momentum only has the time component and no spatial components. The time component is the car's energy. Since the car doesn't view itself to be moving in its own reference frame, its energy is completely in the form of rest mass energy, E equals mc squared. According to Einstein, the car is moving. We can see that the car does have some momentum in the x direction. The time component of the form momentum, the energy, has also increased, because gamma is greater than 1 for a moving object. This means that the car has both rest mass energy and kinetic energy from its motion. But in both cases, the mass of the car is constant and unchanged. Even though Einstein sees the car with more energy, he also sees it with more x momentum, which has a negative sign in this formula. And the extra energy cancels out with the extra x momentum to leave the mass constant. It's the same rest mass that the car would observe in its own reference frame. But why do we care about the form momentum? One of the reasons form momentum is so important is because form momentum is conserved. If you recall Newtonian physics, the law of conservation of momentum tells us that if we add up all the 3 momentum vectors of objects before a collision and add up all the 3 momentum vectors of objects after a collision, then the results should be the same. For example, if 2 particles with equal momentum in the x and negative x directions collide, their total net momentum is 0. This means that their total net momentum after the collision must also be 0. In special relativity, since we found that energy and momentum can mix together when we change reference frames using a Lorentz transformation, if we want a proper relativistic conservation of momentum law, we must use 4 momentum vectors, including both energy and momentum. Let's look at an example of 2 objects colliding together from opposite directions on the x-axis. After the collision, the objects will stick together. The first object has 4 momentum p1 with 5 energy units and plus 3 x momentum units moving to the right. The second object has 4 momentum p2 with 5 energy units and negative 3 momentum units moving to the left. The resulting object after the collision must have 4 momentum p3 that equals p1 plus p2. This means that p3 has 5 plus 5 equals 10 energy units and 3 minus 3 equals 0 x momentum units, so the object is stationary in space. However, the 4 momentum of the resulting object is not 0 overall. It still has 4 momentum in the time component, which measures its rest mass energy. Interestingly, if we calculate the mass of each of these objects using the mass-energy-momentum relation, the total mass of the objects before the collision is 4 plus 4 equals 8 mass units, but the mass of the particle after the collision is 10 mass units. This shows us that in special relativity, the rest masses of individual objects is not a conserved quantity before and after collisions. We need to remember to look at conservation of form momentum as a whole instead, not just conservation of individual rest masses. So we've seen that the derivative of 4 position s with respect to proper time tau gives us the 4 velocity u. It's probably not surprising that if we take the second derivative of 4 position, which is the first derivative of 4 velocity, we get another vector called the 4 acceleration, denoted by capital A. Now, I'm not going to go into a ton of detail with 4 acceleration because I'm actually going to cover acceleration in special relativity in great detail in the Relativity 105 videos, so you can watch those videos to learn more. But I'll do a quick derivation of the formula for 4 acceleration, and you can pause the video if you want to look at it. To take the derivative of the 4 velocity, we use product rule to get 2 terms, one with the derivative of gamma and the other with the derivative of this vector. The vector derivative is easy if we use chain rule on the tau derivative to get the t derivatives times gamma. The derivative of the first component goes to 0, and the rest gives us the non-relativistic acceleration 3 vector small a multiplied by gamma. For the other half of the product rule, the derivative of gamma with respect to tau can be changed to d gamma by dt times dt by d tau, using chain rule. And since this is just the definition of the 4 velocity again, the complete formula for 4 acceleration is d gamma by dt times big U plus gamma squared times little a. It can be shown using chain rule that d gamma by dt is gamma cubed times little a dot little u all over c squared, with a minus sign in front. Now, the reason that this minus sign is here is because I chose to use the mostly minuses convention for the Minkowski metric, where a position basis vector dotted with itself gives a -1. Because of this, the formula axux plus ayuy plus azuz is actually the negative of the little a vector dotted with little u. If we had used the mostly pluses convention, where a position vector dotted with itself gives +1, then this negative sign would be a plus sign instead. So this is something to keep in mind if you see this formula in textbooks or websites with a different sign convention. So this is the formula for the 4 acceleration, and if we like, we can write out the components of the 4 acceleration as a sum of 2 column vectors, which gives us this. So the formula for the 4 acceleration vector is actually quite ugly. The most interesting thing about the 4 acceleration big A is that it is not necessarily parallel to the 3 acceleration small a in the spatial dimensions x, y, z. If the dot product small a dot small u is non-zero, then the 4 acceleration components in x, y, z actually get another term in addition to the standard 3 acceleration small a. So we now have 4 velocity, 4 momentum, and 4 acceleration. The last vector we'll talk about is the 4 force, capital F, which is the rate of change of 4 momentum with respect to proper time tau, where 4 momentum is equal to mass times 4 velocity. If we assume mass is constant, then we can pull mass in front of the derivative, and the derivative of 4 velocity we know is just the 4 acceleration big A, which we've already calculated. So the famous equation F equals ma is actually 4-dimensional in special relativity. It's worth noting that the time component of the 4 force vector is the derivative of the time component of momentum with respect to proper time. Since the time component of momentum is energy, this is the derivative of energy with respect to time, which is power. So the time component of the 4 force is a power term. So in summary, in this video we learned about several 4 vectors in special relativity that all inertial frames agree on. We started with the 4 position, big S, which in previous videos we called the spacetime separation vector. And this can be used to give us a notion of proper time tau when we take the Minkowski length of a time-like 4-position vector. We learned about the 4 velocity big U, which is d big S by d tau, and we learned that the Minkowski length of the 4 velocity vector is always the speed of light c. For massive objects, the 4 momentum big P is defined as mass times the 4 velocity. The time component of the 4 momentum is energy. However, for massless particles like light, we have a special definition where the particle's energy equals its momentum times the speed of light. The 4 acceleration big A is the second derivative of 4 position, and it is not necessarily parallel with the non-relativistic 3 acceleration in the spatial dimensions. And finally, we have 4 force, which is the derivative of 4 momentum with respect to tau. The time component of 4 force is power. All of these 4 vectors are invariant. The geometric vectors themselves are agreed upon by all inertial reference frames, but their components will look different in different inertial reference frames. In order to change between the components of these 4 vectors in different frames, we can transform the basis vectors using a Lorentz transformation, and transform the vector components with the inverse Lorentz transformation, just like we saw with the 4 position in previous videos. We know that this is possible for all 4 vectors because all 4 vectors are written in terms of a spacetime basis. And remember, basis vectors and vector components are 2 sides of the same coin. When we change our spacetime basis in one way, the 4-vector components will change in the opposite way because vector components are contravariant. So anytime we change our spacetime basis using a Lorentz matrix, we know that we can change the components of any 4-vector using the inverse Lorentz matrix by the rules of contravariance and covariance.